and Assalamualaikum. Our presentation is about metallic bonding and band theory, that especially for aluminium. This presentation is for code subject CHM361 and our lecturer is Dr. FATIN HAZIRAH. Before we start to proceed to our next slide, I would like to introduce our group members. Overall, we have 5 group members that include Diana, Maz, Zulaika, Ayu and Batrisha.
Before we jump to our presentation, let me state our 3 objectives, which are to explain the concept of metallic bonding in aluminium in terms of the localized valence electrons and positively charged metal ions. The second one is to describe the electronic structure of aluminium using the modern band theory approach. And the last one is to illustrate how the overlap of 3s and 3p atomic orbitals in aluminium leads to the formation of energy bands. So what are we waiting for? Let's go.
Okay, before we start with further information, I would like to introduce what is metallic bonding and how it's related to aluminium metals. Metallic bonding and aluminium metallic bonding is a type of bonding found in metal, where positive metal ions are held together by a sea of delocalized electrons that move freely between them. This shared electron acts like a glue, giving metal their strength, shine and ability to conduct heat and electricity. In aluminium, metallic bonding is especially strong. Aluminium atoms release their outer electrons into the electron sea, allowing the metal to be shiny, lightweight, easy to shape and a good conductor. This is why aluminium is so useful in things like foils, cans and aircraft.
Alright, let's move how the electron sea model concept works in bonding metals such as aluminium. In aluminium, these atoms are arranged in closely packed and regular lattice. Each aluminium atom has 3 valence electrons and these electrons are not held tightly by the atom. When the aluminium atoms come together, they lose their valence electrons and become positive aluminium ions. Therefore, the lost electrons form a sea of delocalized electrons that move freely throughout the entire metal structure. These electrons are shared by the aluminium ions and are not attached to any one of the atoms. The positive metal ions are held together by the strong structure attraction between them and negatively charged electron sea. So we can see how this model helps explain why the aluminium is a good conductor, right? I mean, the good conductor of electricity and heat, and why it is strong but still malleable and ductile.
Aluminium is a metal and it exhibits metallic bonding. Each aluminium atom releases 3 valence electrons, forming positively charged aluminium ions. These electrons become delocalized, meaning they move freely throughout the metal lattice. The strong attraction between the delocalized electrons and the positive ion hold the structure together, forming the metallic bond. This bonding is responsible for aluminium high electrical and thermal conductivity, malleability, and strength. Aluminium has a fast centrocubic or FCC crystal structure. In this structure, the atoms are arranged in closely packed lattice. In each atom is surrounded by 12 neighboring atoms, which makes the structure very stable. The properties of aluminium are largely influenced by this structure. It has good electrical and thermal conductivity, is malleable and ductile, and is strong yet lightweight, making it ideal for many applications in construction, transportation, and packaging. Looking at the unit cell, aluminium has atom as the corner on the face of the cube. There are 8 corner atoms, each contributing 1/8 of an atom to the unit cell, and 6 face atoms, each contributing 1/2 an atom. Adding this together, the unit cell contains a total of 4 atoms.
Next, let's go to the band theory of aluminium with modern view. Aluminium has an atomic number of 13, with the electron configuration young 3s to 3p1.
In the classical metallic bonding model, metals are described as positive ions surrounded by a sea of delocalized electrons. While this explains metallic behavior qualitatively, a more detailed understanding is provided by the modern band theory as discussed in Chapter 4 of the CHM361 lecture notes. The modern view of metallic bonding, developed from quantum mechanical principles by scientists such as Arnold Sommerfeld and Felix Bloch, explains how electrons behave in solids using energy bands rather than localized bonds. In solid aluminum, the outer 3s and 3p orbitals from many atoms overlap extensively. This overlap causes discrete atomic energy levels to split and form continuous energy bands, specifically the valence bands and the conduction bands. For aluminium, the valence band is partially filled, meaning there is no significant energy gap between occupied and available energy levels. As a result, electrons can move freely throughout the metal when an electric field is applied. This free movement of electrons accounts for aluminium's high electrical and thermal conductivity, as well as its characteristic metallic luster. Thus, the modern band theory provides a quantitative explanation of metallic bonding in aluminium, complementing and expanding upon the classical metallic bonding model.
So let's move on to our next point for application metallic bonding of bond theory aluminium. Aluminium has wide industrial application because of its unique combination of properties such as being lightweight, strong and corrosion resistant, and highly versatile. In the aerospace industry, aluminium is extensively used in aircraft structure, wings and fuselage components due to its high strength to weight ratio, which improve fuel efficiency and performance. In the construction industry, it is commonly used for window frames, roofing, cladding, and structural components because it is durable, require low maintenance, and resists corrosion even in harsh environments. In the electronic industry, aluminium is valued for its excellent thermal and electrical conductivity, making it ideal for heat sinks, wiring, and electronic casing. While in healthcare, aluminium is used in medical equipment, hospital furniture, and pharmacy packaging because it is lightweight, non-toxic, and easy to sterilize. In the energy sector, aluminium plays a key role in power transmission lines, solar panel frames, and wind turbine components, helping improve energy efficiency and sustainability. Overall, aluminium's reliability, durability, and adaptability make it one of the most important materials across modern industry. So, let's move on to our next point of applications, metallic bond theory of aluminium. Electronic recycling and sustainability have become increasingly important as the use of electronic devices continues to grow worldwide. Research on new compounds and advanced recovery technique helps extract valuable metals such as gold, silver, and copper from electronic waste, reducing the need for environmentally damaging mining activities. Aluminium plays a key role in electronic devices as it widely used in casing, heads, heat sinks, and internal components due to its lightweight nature, good conductivity, and corrosion resistance. One of aluminum's major advantages is that it can be recycled rapidly without losing its properties, making it highly suitable for sustainable manufacturing. Efficient recycling of aluminum and other metals from e-waste conserves natural resources, save energy, reduce landfill waste, and lower greenhouse gas emissions. Overall, electronics recycling support environmental protection while promoting a circular economy in which valuable materials are recovered and reused instead of discards. That's all.
Okay, we are already in the last part. In conclusion, metallic bonding play a key role in giving material their unique properties. In aluminium, the strong attraction between positive metal ion and the sea of delocalized electron make it shiny, flexible, and a good conductor of heat and electricity. Because of the type of bonding, aluminium is both strong and lightweight, making it an important material in many everyday and industrial application. So that's all from us. Thank you.
This is our reference page. We already use 8 different article or others material to be included as our citation. And finally, thank you for the cooperation to listening for our presentation. Thank you. Bye.